Hello everyone, welcome back to the lecture of alternative forms of pull-ups. In the last lecture, we have seen MOS transistor, operation, characteristics and its use as pass transistors. Now, its pass transistor use we are going to see in the circuit modeling. So, if a pass transistor is used in the circuit or MOS transistor is used in the circuit, what should be the load element? And what are the different elements can be possible used for the load elements? As example here we are seeing as inverter circuit. So, in this lecture you are going to understand the alternative forms of pull-ups. The contents for this are, you are going to see pull-up forms with load resistance RL, with NMOS transistors of both depletion and NMOS transistors as load devices and PMOS transistor as the load device because it is acting as complementary transistor for the load. First, let us see what is pull-up. What is the meaning of the pull-up? In our VLSI circuit, while constructing a gate or a logic function with the CMOS, we are going to use, or with the CMOS or with the NMOS, we are going to use functionality network and load network. This is load network. Load network is always called as pull-up network where it makes the output from low to high. So, always output it makes from low to high. Whenever the output wants to reach to VDD, this pull-up network is used. That's why the name is called as pull-up. This pull-up network is pulling V out to the upper value in the circuit. That is VDD value. So, V out is equal to VDD when the pull-up network is in the on condition. Similarly, when pull down condition is non condition, then V out is pulling down to the value of the 0. That's why its name is called as pull down network. And whereas this pull down network will be defined the functionality. So, coming to this pull up network, what are the different devices can be used as the pull ups? We are going to see now. And in this mode, for the seeing of different load devices, we are taking the example of inverter for the understanding of the pull-up devices and its effects and its characteristics. So, this load device may be always either RL or NMOS transistor can be used as a load or PMOS transistor can be used as a load. When NMOS is used, it can be enhancement transistor or it can be depletion transistor. For the PMOS, it will be always used as enhancement transistor. And for the functionality, here always NMOS transistor is used in the VLSI circuits. So, pull down is always NMOS, pull up may be one of these devices. That means with load resistance RL, with NMOS either enhancement or depletion, with PMOS enhancement type. So, these may be 4 types. Therefore, we are going to see now 4 alternative forms of pull-ups. That is, load resistance RL as a pull-up and NMOS depletion mode transistor as a pull-up and NMOS enhancement mode transistor as a pull-up and complementary transistor as a pull-up. Since functionality is implementing with NMOS, here complementary transistor is always PMOS. Therefore, PMOS transistor as a pull-up. Let us see each and every one. The first one as load resistance RL as a pull-up. So, inverter we are taking. This is the circuit diagram for an inverter with load is taking as RL. That means resistance. So, this is used as a switch which is operated based on the value of the input value Vin. So, when Vin is 0, switch is off, Vin is 1, switch is on. So, it is always NMOS transistor. So its basic connection is input is connected to a switch, that is NMOS transistor at the gate terminal, and the source terminal of this NMOS transistor is connected to the ground or VSS, and a drain is connected at the output. From the drain of this NMOS transistor to VDD, the load device is connected. This load device is RL here. Now, output is taking from the joint connection of load device and drain terminal of the NMOS transistor. Here, because of using the resistance in the circuit, it occupies more space here, therefore it is not preferable, but as a first case we are seeing this. Let us check the operation of this inverter with the resistive load as the pull-up device by taking the input value as 0 or 1. So let us take first input as 0. First case Vin is equal to 0, and take the transistor name as a T1 here. So for input of 0, T1 is off, since that is the NMOS transistor. Now what will happen? It is acting as an open circuit or open switch. That means when it is open, Vout is not having a path to discharge to the VDD. So it will be charged to the VDD value, or Vout is connected to the VDD. So in the sense, because it is an open circuit, here the current is equal to 0. The current is equal to 0. Since current is equal to 0, there is no drop across RL. Therefore, Vout is passed to VDD. What is the Vout equation? Vout equation is VDD minus RL into I in the circuit. Since transistor is open circuit, I is equal to 0. Therefore, the product of RL into I is equal to 0. Therefore, VDD minus 0 is equal to VDD only. So, Vout is equal to VDD for the case of Vin is equal to 0. So, low value, high value. It is acting as inverter. Now, let's see when Vin is equal to VDD, what is the output value. So, when Vin is equal to VDD, here if VDD is applied, what will happen to the T1? T1 is on. T1 on means, T1 switch is on means, it is acting as short circuit or short switch. When the switch is in the short, then Vout is connected to the VSS because it is having a path to discharge if there is any CL element in the output. So, since it is off, it is on or short, then I is not is equal to 0 because it is on, there is a short connection, I is not is equal to 0. So, it is equal to maximum value. It passes in the circuit as a maximum amount of current. Now, what will happen to the Vout now? Vout is equal to, equation is VDD minus V into RL. Since I is equal to not 0, it is maximum. So, it is also approximately equal to VDD. Therefore, VDD minus approximately equal to VDD is approximately equal to 0. So, when input is equal to VDD, output Vout is equal to 0 value. So, it is also acting as the inverter case. So, for Vin, for V0 and VDD values, output is producing the inverter. So, it is acting as an inverter and load element is using to reach output from 0 to high value. This is the operation of the inverter with RL as the load device. In the resistive pull-up device, only the problem is because of RL is used in the load, in the ICs, it will take more space. So, it is not preferable. So, that resistance is replaced with MOS transistor. In the first, they have chosen as NMOS depletion transistor as the load device. When this is taken as the load device, what will happen? NMOS depletion is taken and its gate is connected to the source, in the sense VGS is equal to 0 always because the difference between these two is 0 always. But NMOS depletion transistor is switch on for VGS is equal to 0, means this NMOS transistor is always in the on condition, means just a resistance is replaced with always on transistor of the type of NMOS depletion transistor. And whereas for the pull down transistor, it is switch on only when Vin is greater than of Vt value. So this switch will react as per the input voltage, but this is in the on condition. So this load device is equivalent to just simply a resistor, but instead of resistor taking as the MOS transistor. Let us check its operation. When Vin is connected to 0, what will happen? When Vin is connected to 0, since it is less than of Vt, this is let's check it operation. When Vin is equal to 0, transistor T1 is off, since T1 requires minimum of Vt value. T1 is off. And T2 is load device. It is always in the on condition. So T2 is on. Since T2 is on and T1 is off, what will happen? Open circuit in the pull down path and closed circuit in the pull up path. Therefore, Vout is equal to VDD value. Vout is equal to VDD value. For this Vin is equal to 0. Now let us take Vin is equal to VDD value. What will happen? So when Vin is equal to VDD, T1 is on and T2 is always on. Because of on, what will happen? Vout is having a path of connecting to the ground. So therefore Vout is equal to discharging, but it is not fully discharged because of having a short connection here. There is current flowing in this circuit and it is just replacement of some small resistance. So some voltage will be dropped across this resistor, means across this pull up path. VDD minus this VR is going to be output. And since I is maximum, this VR is going to become the maximum value. So therefore, Vout is equal to VDD minus VR and VR is maximum. So therefore, this difference, this is not is equal to VDD and it is maximum only. Therefore, this output Vout is going to be equal to 0, not fully 0. This is equal to 0, not fully 0. So when we see the characteristics of this, we can observe this Vout is equal to VDD for Vin is equal to 0 and for the output equal to 0, approximately equal to 0 for the Vin is equal to VDD case. Means output is not full 0 for this circuit. When we represent the output and input values as a characteristics, when input is taken on x-axis and output is taken on the y-axis, input is changing from 0 to higher value, that is VDD, then the output is plotting like this. So when input is 0, output is starting with the VDD, there is no problem. Output is full VDD, which we have seen just now as the operation, and it is transmitting, it is appearing as, and it is reducing. At the VDD, it is producing as non-zero output. That means it is not equal to 0. There is some voltage drop in the output. So for Vin is equal to 0, output is equal to VDD, and for Vin is equal to VDD, output is approximately equal to 0, not is equal to 0. And here one more problem is there. When Vin is equal to logical 1, the power dissipation is high in this circuit because there is a short path from the VDD to ground. That means in this inverter, when Vin is equal to VDD, Since these two are on, there is a short path between the two power supply rails. Because of this, higher power dissipation is the problem. The same problem is existing in the inverter with resistive load also. Means in the behavior wise, resistive load and this inverter with NMOS depletion mode pull up are same, but only the difference is the area occupied by this transistor is less when compared to the resistor in the IC versions. Therefore, to reduce this power dissipation and to have full outputs at both levels, this load device is changed and it is changed as NMOS enhancement transistor and observe the operation. Now let's check when this is replaced with NMOS enhancement, what will happen to the circuit. The circuit construction is T1 transistor, functionality transistor, T2 transistor, now it is NMOS enhancement transistor. So now what will happen? Whenever the gate of the enhancement transistor is connected with 0, this is off. But this should be used as load device. Load device means it should be on whenever pull up is required. So therefore, to make this on, VG for this transistor is connected with VDD. So therefore, this is also using as load and always on transistor connection only. And this is the switch acting on or off depending upon the Vn value. So T1 is switched on when this input value is greater than of threshold value only. And here it is switched on when its gate voltage is greater than of the Vt. So we have taken VDD value. Now let's check its operation for the both logic 0 and logic 1 of the inputs. Let us take Vn is equal to 0 first. Vn is equal to 0 and T1 transistor and T2 transistor. Now what will happen? When Vn is logic 0, T2 is always on and T1 is off. Since T1 is off, it is acting as the open circuit and Vout is reaching to the VDD. And since it is NMOS enhancement transistor, it will work as NMOS pass transistor. Just now we have seen pass transistor at one end, at the source end, if VDD is connected, but that is passed as VDD minus VTN to the other end. So this T2 is acting as a pass transistor for the input of VDD is applied at one side. So other side it will pass as VDD minus VTN. So when Vn is equal to 0, Vout is equal to VDD minus VTN. It is not is equal to exactly VDD value for the Vn is equal to 0 case. Now let us take Vn is equal to VDD case. Now what will happen? T1 is going to be switched on and T2 is anyway switched on. So T1 is on and T2 is also on. So here both are on means there is a short connection from VDD to ground and Vout starts discharging through the transistor T1 and it doesn't reach to full 0 because of some loss of the value in the second stage. So Vout is approximately equal to 0. This is the same case which is happening in the NMOS enhancement and depletion mode inverter circuit. So for Vn is equal to VDD, output is approximately equal to 0 and for Vn is equal to 0, output is equal to VDD minus VTN. So here both logic levels are not full swing. Both logic levels are not full swing. Let us see these two values as a graph. See here, when Vn is equal to 0, output is VDD minus VT of the second transistor, whereas it is VDD. So this is a drop reduced at the output. Similarly, for the input is equal to VDD, it is approximately equal to 0, but it is not as equal to 0. It produces non-zero output. This is the characteristics of NMOS inverter with pull-up of enhancement NMOS transistor. And here the power dissipation problem is still existing since there is a short path when Vin is equal to 1. When Vin is equal to 1, short path is existing, so power dissipation is not reduced, and moreover because of replacing depletion with enhancement transistor, output for the high also it is degraded. This is the remark of this enhancement NMOS transistor as the pull-up device. Now let's see the alternative solution to this of the NMOS transistor as a pull-up, even though it is a depletion and enhancement transistor. Let us discuss the problem with this circuit. The problems with this circuit are, the first one is power dissipation. Power dissipation is not reduced when compared to the previous circuit because here also static path existing. And the outputs are also not full swings. That means output 1 is reduced and output 0 is also reduced. And one more thing required is, at the gate potential we need to use one more power source. So if gate is VDD, it is okay, we can use the power supply as a C. If it is other than VDD, if it is not equal to VDD, then we need to use one more extra power supply here. So 2 power supplies are required if gate supply is at the gate is VDD not connected. That means outputs are not full swing and gate power supply is required if it is not equal to VDD and static power is still existing in the circuit. These are the problems with this circuit. To rectify that, this load device is replaced with next solution as PMOS transistor. Let us see the load with PMOS transistor. See the fourth alternative pull-up, that is complementary transistor as the pull-up. Since the NMOS transistor is using as functionality transistor in the pull down always, complementary to this NMOS is PMOS. So when PMOS is used as the load device, the circuit of NMOS inverter will be look like this. Since both NMOS and PMOS are using complementary, it is also called as CMOS inverter. It is called as CMOS inverter. So therefore, from now onwards, this shouldn't be calling as NMOS. It is CMOS inverter. And here load device is PMOS transistor and functionality device is NMOS transistor. For these two transistors, at the gates, same signal is applied, that is input signal. At the drains of these two transistors joined and output is taken from that point, and source of the NMOS transistor is connected to the lower potential and source of the PMOS transistor will be connected to the higher potential always. Let us check its operation and characteristics and the problems which are present in the previous circuits, whether they are removed or still existing, and what are the new problems existing in this CMOS inverter we will see. So this pull down transistor is switched on when Vin is equal to VDD, since the threshold voltage of this is positive, and when Vin is equal to 0, this pull up device is switched on. Means for input of 0, 1 transistor is on, for input of VDD other transistor is on. Let us check its operation. For input is equal to 0 and input is equal to 1. Let's take Vin is equal to 0 and take the transistor T1 and transistor T2. When Vin is equal to 0, since PMOS transistor is on, so T2 is on and T1 is off. Since T1 is off, it is open path and T2 is on, the pull-up is short path. Therefore, output is equal to VDD. Vout is equal to VDD. And we know already, this is a PMOS pass transistor. At one end, it is connected as a VDD. So, this PMOS pass transistor passes full VDD. Therefore, Vout is equal to, there is no loss, full output, VDD is the output. Now, connect Vin is equal to VDD at the input. Now, what will happen? So, since Vin is equal to VDD, T1 transistor is on and T2 transistor is off. Since T1 is on and T2 is off, there is no pull-up path. There is no pull-up path. This is the open connection. Because of that, VDD is not connected to the Vout. So, Vout is having a path to discharge. So, therefore, Vout is equal to completely discharged to the VSS, or it is 0 if we have taken VSS as the 0 value. So, when Vn 0 full output, Vn 1 full output. Therefore, both outputs are full swing. Both outputs are full swing. Full values. The problem which is existing in the all three cases of the pull-ups is eliminated here by taking a complementary transistor as the pull-up, first problem. And second one is, when Vn is equal to 0, only PMOS is on and NMOS is off. That means when Vn is equal to 0 value, and when Vn is equal to 1, PMOS is off and NMOS is on. Means either of the transistor is on condition at particular time. Therefore, there is no short path between the VDD and ground for any value of the input. That means, for one case PMOS is on and NMOS is off. This is the equivalent. For one case PMOS is on and NMOS is off. This is the case. So, therefore, in both cases, the open connection is there. Therefore, there is no static power. That problem is also eliminated. Power dissipation is less in this because of there is no direct path connection. Let's see its characteristics as graphical representation of outputs and about power dissipation. So, VDD is the output when Vin is equal to 0, and when Vin is equal to VDD, output is equal to 0 value. So, the characteristics are having a full output VDD and 0 value. And since it is having of absence of static path, static power dissipation is 0. But the problem with this device is, for the P and N, both transistors, if we have taken the similar dimensions, PMOS transistor is smaller. The problem is, if you are taking the P and N channel transistors or PMOS and NMOS transistors of equal dimensions, then P is slower than the NMOS transistor. So, to make P faster, the sizes of the P and N are different and P should be somewhat larger than the NMOS. We will discuss this in detail in the CMOS inverter lecture. So, different sizes of the P and N are required and there is no static power dissipation and output values are full swing. These are the characteristics of this device, a circuit with complementary transistor as the pull-up. Now, let's check our understanding with the help of this quiz. In CMOS logic circuit, the NMOS transistor acts as NMOS. What we have seen in the CMOS. CMOS means in the CMOS inverter. First we have seen load as the PMOS and transistor, NMOS as the functionality device. So, pull down network is NMOS and pull up is with the PMOS. Therefore, NMOS transistor is using as pull down network. Then in NMOS inverter configuration, depletion mode device is called as NMOS inverter configuration. What is the NMOS inverter configuration? So NMOS inverter with depletion and enhancement can be used as the load, but here depletion mode transistor is given. So NMOS inverter with depletion mode transistor with VGS 0 output and ground and VDD supply with the input. Now this is the pull up device and it is the pull down device. So in the NMOS inverter with the depletion mode device is again the pull up transistor only. Next, in a basic inverter circuit, dash is connected to the ground. Basic inverter circuit means a circuit with RL as the load device. This is the basic inverter circuit calling as. And here, dash is connected to the ground. Which is connected to the ground? Ground pull down device is connected. In the pull down device, NMOS is used. In particularly NMOS, what terminal is connected? So source, gate and drain are connected like this. Therefore, to the ground, source is connected. So answer is source. Then in inverter circuit, dash transistors is used as load. So in the inverter circuit, which transistor is used as the load? We have seen RL as a load, enhancement as a load, depletion as a load, and complementary transistor is also as a load. So enhancement mode, depletion mode, all the mentioned, none of the mentioned, because we can use these two in the NMOS. Therefore, all the mentioned can be used in the inverters as the load devices. Take these questions as assignment questions, that is, explain the operation of CMOS inverter and derive the transfer characteristics of CMOS inverter. Compare all the pull-ups, alternative pull-ups, and compare the NMOS with CMOS, and compare NMOS enhancement pull-up with the NMOS depletion pull-up, so that you can get the clarity on this topic. Follow the textbook of Bucknell once again, that is Essentials of VLSI Circuits and Systems by Bucknell for understanding of this topic. What we have seen till now, that is summary. We have seen different forms of pull-ups. Those are of 4 types. One is load resistance, and second one is NMOS depletion, third one is NMOS enhancement, and next one is complementary transistor, that is PMOS transistor. And those figures are represented here with load resistance, with NMOS depletion, with NMOS enhancement, with PMOS transistor, that is complementary transistor. What is the comparison of all these and what are the remarks? For the first 3 cases, static power is existing. For the 4th case, static power is 0. So, first comparison is power dissipation. Static power is not 0 here. Here also static power is not is equal to 0. Here also static power is not is equal to 0. But static power is equal to 0 here because of no static power. Then output load values or output values at the Vout output values. Output values are Vout is not exactly equal to 0 in this case, and in this case also Vout is not exactly 0 for the low value of the output when Vin is equal to logic high, and here Vout is not exactly equal to VDD and not exactly equal to 0 for the Vin of all the cases for the 1 and 0, and but here in the CMOS Vout is equal to full VDD and is equal to full 0 for the 2 values of the inputs. So this is about the logic levels, power dissipation and logic levels. Then about space, the first is since because of RL it is taking the more space when compared to all the other 3 pull-ups, and the switching device or pull down device is taking the same size or same area for all the 4 devices, 4 circuits. Then for the depletion mode and enhancement mode of the same NMOS type, extra power supply is required for the enhancement NMOS load device to make into switch on condition, and if it is not equal to VDD. And the problem with this PMOS is, since PMOS is slower when compared to the NMOS, the device size shouldn't be the same for the NMOS and PMOS devices. PMOS should be larger than the NMOS device. So this is the comparison of all the 4 pull-ups. I hope you understood this. Alternative pull-ups. We will see NMOS inverter in the next lecture in detail. Thank you.